Welcome and thank you for joining. In this lesson, we'll explore the continuity of a function. Remember that for a function to be continuous, we should be able to draw its graph without having to lift the pencil. So there are no breaks in the graph. By definition, algebraically speaking, we're going to say that a function is continuous at every value x equals a if three conditions are true. Condition number 1, f of x must be defined at x equals a. Condition number 2, the limit at x equals a exists, which means that when x approaches a from the left-hand side or the right-hand side, the value of the function or the values of y will approach the same number. Condition number 3 is pretty much connected to conditions 1 and 2. So we want the value of f of x to equal the limit of f of x at a. Or in other words, f of a must be equal to the limit as x approaches a of f of x. So below you see the graph of a function, and we are going to discuss the continuity of this function at a. As you can see in here, we can draw the graph of this function without lifting the pencil. And the value of the function at a equals f of a. When we look into the limit of this function, we approach a from the left-hand side. And as you can see, as we approach a from the left-hand side, the values of the function are approaching f of a. When we approach a from the right-hand side, the values of the function are approaching again f of a, which means that the limit of the function at x equals a equals f of a. When we say the limit of the function at a equals f of a, it means that the values of y are following the trend that is set on this graph, so they are aiming towards the same y value. So since the limit of the function and the value of the function at x equals a are the same, we're going to say that this function is continuous at a. Now, if any of the three conditions are unsatisfied, then therefore the function will be discontinuous. So first, we're going to take a look at an example where a function is continuous and discuss the continuity algebraically. For example, the limit as x approaches 2 of x, we have to discuss or find the limit of as x approaches 2 of x squared and discuss the continuity of f of x equals x squared at exactly x equals 2. Now we know this function is continuous and we are very familiar with the graph of it, which is the graph of a parabola. So it's a quadratic function. So the vertex of this quadratic function will be exactly at 0, 0. At x equals 2, we know that the value of the function will be equal to 4. So this is the point that we are discussing, x equals 2. So first, let's discuss the limit. We're going to say that the limit as x approaches 2 from the left-hand side of x squared is equal to 2 from the left-hand side squared about 4. The limit as x approaches 2 from the right-hand side of x squared would equal 2 from the right-hand side squared equals about 4. So therefore, we're going to say that the limit at the given point exists. And more specifically, we'll write limit as x approaches 2 of f of x, or limit as x approaches 2 of x squared, is equal to 4. Now, the function at the given point, so at x equals 2, or f of 2 is equal to 2 squared or 4. As you can see, the value of the function at the point and the value of the limit at the point are equal. Therefore, we're going to say that the function is continuous at the point that we discussed, so at x equals 2. Obviously, this is the continuous at any x and any real number x, right, throughout its domain. Now, let's take a look at a more interesting side of continuity. So, when is a function discontinuous? So, let's discuss discontinuity. There are three types of discontinuities that we discuss in this course. Number one, removable or point discontinuity. So we group them together in one bigger group because they're kind of similar and they kind of appear together. Removable discontinuity happens when the graph of a function will show a hole or a break in the shape of a hole, which means that the function will have no value or will be undefined at x equals a. The reason why we call this removable discontinuity is because these types of discontinuities happen mostly in rational functions when we remove a restriction. Remember that when a restriction is removed in a rational function f of x over g of x, then one of the vertical asymptotes is removed because a restriction in rational functions translates to an asymptote. So when a vertical asymptote is removed, it will leave a hole on the graph of the function. And this is where the name removable discontinuity comes from. Now, as you can see, in removable discontinuity, the limit of the function at x equals a exists. And that is because when we approach a from the left or the right-hand side, the estimated values of y would be equal to the same number, which we are calling the number L. However, the function is undefined at a, which means that f of a is undefined, but the limit as x approaches a of f of x exists. Now remember that there were three conditions for the functions to be continuous. F of a should be defined, the limit must exist, and the two of them must be equal. So because one of the rules is broken, it means that the function is discontinuous. Now sometimes it may happen that a function may show a hole on the graph. However, the function is defined at x equals a. This is usually happening in piecewise functions that are made of one piece or one equation that has a removable asymptote and one piece that is probably just a single point. So in this case, we're going to say that the value of the function at a exists and it is equal to f of a. As you can see here, if we were to find the value of the function at a, that would lead us to this y value. The limit of the function as x approaches a from the left-hand side, let's take a look at a from the left-hand side, is equal to the value of L. Remember that we cannot say the limit equals f of a because the limit is not found exactly at a, it is found close to a. So the limit gives an estimated value of the function if the function were to continue the trend, the main trend that is set by its graph, by the general behavior of the y values. So we're going to say that on the left-hand side, the limit is L. And on the right-hand side, the limit is also equal to L. So you see, you approach a from the right-hand side, the values of y are going towards L, which means that the value of the limit of the function will exist because the value of the function as x approaches a from the left and the right is approaching the same value L. Now, condition number 1 for continuity is satisfied because the limit of a function, the value of a function at a exists. The limit of the function exists. However, notice that the value of the function at a is different than the limit of the function at a. So the third condition is left unsatisfied, and that is what creates a point discontinuity. Now, the next type of discontinuity is what we call the jump discontinuity. This is my favorite type of discontinuity. It's so easy to recognize and so easy to understand and explain in the meantime. So jump discontinuity, as you can see in here, looks like the graph shown on this picture. So, in a jump discontinuity, as you can see, to draw the graph, we have to jump vertically from one point to another to continue drawing the rest of the graph. Now, I want you to think, where can these type of functions be, most typical? These type of functions are piecewise functions. So this is where you have some function f of x that is made of two different equations that exist in two different domains. For example, this function exists in the domain for x less than a, and this is the function that exists in the domain for x bigger than a. Now, the function is obviously discontinuous because there is a break in between the two pieces, and to go from one part of the function, from one piece to the other, we need to make a vertical jump. Now, what happens to the three conditions here? If you look at the value of the function at x equals a, then we're going to say that the value of the function at a doesn't exist. So, which means that we are left with an unsatisfied condition here in the very first step. So we know this because if we go at x equals a and try to reach the graph of the function, we do not see any definite point here. Now, when we look at the limit of the function when x approaches a from the left-hand side, let me fix this. So let's approach a from the left-hand side. Notice that the values of y, when we are on the left side of a, are equal to L. And when x approaches a from the right-hand side of it, the values of the function are approaching R. As you can see, the left and the right-hand side limits are different. So therefore, we're going to say that the limit at x equals a doesn't exist, because there is no predictable value of y at x equals a. So as we approach x equals a. So both conditions are unsatisfied, so they're undefined, which means that we cannot determine, or the function is not continuous at x equals a. Now, I want you to think, what if instead of having empty circles in here, which we said tell us that the function is undefined at x equals a, so what if one of these points were filled? Okay, so if one of these points were filled, it means that the value of the function at a would exist. So the first condition would have been satisfied. So let's say, for example, it was equal to L. But would that change the type of discontinuity of this function? So even if f of a existed, so even if the function was defined at x equals a, the fact that the limit on the left and the right were different still would create the break on the graph, or the jump discontinuity. Now, if we were to take this a little further, what if the other dot up here was also filled? Now, how would that have changed the type of discontinuity? Well, the type of discontinuity wouldn't have changed still, right? So it would have still been a jump discontinuity. And that is thanks to the fact that the limits on the left and right are different, which means the limit doesn't exist. So it is the limit that actually determines the type of discontinuity, and not just the fact that the function is undefined at that point. However, the difference between having only one of the points filled or both of the points filled will change this to a known function, because if we had both points filled, then it means that the function, this relation would be a known function. It doesn't pass the vertical line test. Okay, so what I want us to take from this example or from jump discontinuity is to understand that jump discontinuity will happen if the limit on the left hand side and right hand side don't agree. So the last type of discontinuity, and this is quite interesting, is what we call the infinite discontinuity. Infinite discontinuity is kind of similar to jump discontinuity because we're going to see a break in the graph of a function. However, the break between, or the distance between the two pieces of the graph of the function will be infinite in size. So as you can see, in jump discontinuity, we had a measurable gap between the two pieces, whereas in infinite discontinuity, we have an immeasurable gap between the two pieces. Now I want you to think, what makes this gap immeasurable? So what makes this gap immeasurable is the fact that one of the pieces of the graph will continue down here to negative infinity. It could have been positive infinity, it doesn't really matter, but it seems that in this case, we're approaching negative infinity. And that's what creates a huge gap in between the two pieces. And this is what makes this type of discontinuity what we call infinite discontinuity. So infinite discontinuity may appear in this shape, or it may also appear in this shape, and this is very popular kind of graph that we have seen before. So in the graph of the function y equals x, the limit on the left is negative infinity and the right is positive infinity. So if either side of the limit is heading towards infinity or negative infinity, that will create an immeasurable gap between the two pieces of the graph, like vertical gap, obviously. So if one side, so the left side, or it could have been the right side, or it could have been both sides, will have a limit that approaches infinity, then that would guarantee infinite discontinuity. Now, infinite discontinuity also happens in graphs like this. As you can see in here, at both ends, the graph will approach positive infinity. However, the graphs will never connect with each other. So they're going to be infinitely close in a way. So it's going to be an infinitely small distance between the two sides of the graph, or two pieces of the graph, or two sides of the limit. So this again presents infinite discontinuity. So these are the main definitions and how discontinuity of a function can be described and explained. I hope you find this useful. I hope this made sense. And in the next video, we'll talk about some examples, so we'll explore some examples together. Thank you for watching, and bye for now.